Alright, hi and welcome back. So in this video, we're going to do a lot of practice with the integration techniques that we've learned thus far. So we've learned the basics of integration and we understand how to do integrals with u-substitution. We have a lot of tools in our toolkit. Now it's just a matter of using those tools and solving problems that are applicable in the real world. But also, if you're taking the AP test, these are some good questions to look at because these are the types of questions you'll see on the exam. So without further ado, we're just going to jump into it. So this is our first question, and it's kind of a word question, so let's read through it. A faucet was turned on at t equals 0, and t minutes later, water was flowing into a barrel at a rate of t squared plus 4t gallons per minute for 0 less than or equal to t less than or equal to 5. How much water was added to the barrel during these 5 minutes? Okay, so we're given a rate of flow. So that's the key word here, rate. And we want to find the total amount of water accumulated, how much was added to the barrel. So we somehow have to translate rate into volume. So if we think back to when we were learning about physics in calculus, we remember that velocity was related to displacement via a derivative. So we took the derivative of position or displacement to get velocity, and to go backwards from velocity to displacement, we would take the integral. So that's what we're going to do here, because we have a rate that we're given, a function which is a rate, and we want to get the displacement or the volume accumulated, the quantity that was added to the barrel. So we're going to do that via an integral. So we'll calculate the integral of t squared plus 4t, and we're going to do this with respect to time, so dt. But importantly, the question asks how much was added to the barrel during those 5 minutes. And again, we're given bounds on t. So given those bounds, we have to make this a definite integral, so a lower bound of 0 and an upper bound of 5. And we know how to solve this. We're good at integrals now, we can solve this no problem. So let's do it. Let's see, integral of t squared. Well, we're going to raise the power to 3, 2 plus 1, 3, and then divide by that new power. And then we'll add to that the integral of 4t. So we add 1 to the power of t and divide by the new power. And we're going to evaluate this from 5 to 0. And we can use the fundamental theorem of calculus for this. So first we'll plug in the 5 where we see a t. So this will be 5 cubed over 3 plus 4 times 5 squared over 2. And from that, we'll subtract the same thing, but now we'll plug in a 0 where we see a t. So 0 cubed over 3 plus 4 times 0 squared over 2. Okay, so we can see that in the second term here, this 0 cubed over 3, that equals 0, and similarly this equals 0. So we can eliminate both of these, and now we're just left with the first two terms to deal with. So the first one is going to equal, well, let's see, 5 cubed is 125 divided by 3, and we're adding to that 4 times 5 squared, so that would be 4 times 25, so that would be 100 divided by 2 is 50. And this is going to be approximately equal to 91.67. So cool, we solved it and we got the number, but a huge part about these problems is the correct units, right? 91.67 doesn't mean anything really right now until we put it back in terms of the question. So let's see, water was flowing into the barrel at this rate of gallons per minute. We integrated with respect to t, which is time, in minutes, so that'll leave us with 91.67 gallons of water. And that should make sense because we were calculating the volume of water accumulated. So our units of gallons should match what the question's asking for. So that's part A. Now we have part B. Find the average flow rate for these 5 minutes. Okay, so again, we're probably going to use this rate of flow because, the question asks about the flow rate. But now we need the average value of a function. So hopefully you remember this formula. If not, we have a video talking about this, the average value of a function. But the formula is 1 over b minus a times the integral from a to b of f of t dt. That's our formula for average value of a function. So now we just have to substitute and solve. So this is going to be equal to 1 over something, but I'll leave that something for now. Integral f of t, that's the easy part, that's t squared plus 4t, which is given to us. And we're going to integrate with respect to time. So now it's just dealing with this b and a thing. And it's just going to carry over from the first part to the 0 and the 5, right? The question asks for the average flow rate for these 5 minutes, starting from t equals 0 to t equals 5. So the limits are easily 0 and 5. So that means a equals 0 and b equals 5. So now we can fill out this denominator here. That would be 5 minus 0. Excellent. So now it just comes down to solving this expression here. So this will be equal to 1/5 integral from 0 to 5 of t squared plus 4t dt. And well, we just solved for this up here, right, in part A. We said that this was approximately equal to 91.67, so we'll just do that substitution. 1/5 times 91.67, and that'll give us an approximate answer of 18.33. Again, we need the correct units here. So now we're talking about average flow rate. So we're dealing with a rate which is in gallons per minute. So we're going to use those same units because we're still talking about rate. So this would be gallons per minute. And that's the end of this first question. So for this question, it's really helpful to know the average value of a function formula. And then the biggest tip is to always make sure you're writing down the units and making sure the units make sense and match what the question's asking for. Awesome. Let's move on to the next question. So this comes from a past AP exam from the year 2000. And it's a similar context to the previous question, but let's read through it. Water is pumped into an underground tank at a constant rate of 8 gallons per minute. Water leaks out of the tank at a rate of square root t plus 1 gallons per minute for 0 less than or equal to t less than or equal to 120. At t equals 0, the tank contains 30 gallons of water, and then we have a bunch of questions. Okay, so what we're going to do is, I like to draw a picture just because it helps me. So what we have is like a little tank here. It'll be a nice little cylinder. And then it's already kind of filled with water. So we'll just kind of shade that in here. But then there's like a little faucet, which is like pouring out water. I guess I'll just extend the faucet a little bit. So this is like pouring water in at some rate. But then there's also a hole here, perhaps, where water is flowing out. So that's sort of our drawing. And then we can write the appropriate rates with the input and output. So the faucet is giving water at 8 gallons per minute. And the water is coming out at square root of t plus 1 gallons per minute. Okay, so now we can start to solve the problem. I like having a picture just to visualize what's going on. So the first question asks how many gallons of water leak out of the tank from t equals 0 to t equals 3 minutes. So we're dealing with leakage only. So that's this function here, square root of t plus 1. And again, we're looking for the quantity of gallons that leaked out, and we're given a leakage rate. So again, we want to go from rate to this gallons, this volumetric quantity. So to do that, similar to the previous question, we'll use the integral function again. So we're going to do the integral of the square root of t plus 1. And we're integrating with respect to t. I'll just zoom in here so we can see it a little bit better. And we're asked how many gallons leaked out from t equals 0 to t equals 3. So those would be our limits. So we're going integrating from 0 to 3. So now we just have to solve this. And how are we going to solve this, you ask? Hopefully you're shouting it out. We're going to use some u-substitution. So we have to choose a good u here. Choosing the square root of t plus 1 may seem tempting at first, but then you'll realize like once we take the derivative of that, there's nothing left to cancel it with. So what happens if we just let u equal t plus 1? Well, then we have du equals dt, and then let's see if we change this integral. So we're still integrating, and then let's just deal with the integrand and handle the limits later. So now we will be taking the square root of u times du, and so that seems like a doable integral. So now let's take care of the limits. So this would be from u equals 1, because we're putting this 0 into this t plus 1, and we get 1. So it goes from u equals 1 to 4. Okay? So we can rewrite the square root as u to the 1/2 power du. And now we can just use the power rule. Sorry about all of the arrows, but it's just the room. So power rule will raise the power by 1. So that'll be u to the 3/2 power. And then divide by that new power, so dividing by 3/2 is the same thing as multiplying by 2/3. So this would be 2/3, and we'll evaluate it from 4 down to 1. And now we'll just plug it in, use the fundamental theorem of calculus. So this is going to be equal to 2/3, 4 times 4 to the 3/2, minus 2/3, times 1 to the 3/2. And now we have to solve this. Okay, so let's handle it separately. 4 to the 3/2. Okay, so 4 to the 1/2 power is 2. That's just the square root of 4. And then 2 cubed would be 8. So this is equal to 2/3, I'll just write it out, 4 to the 1/2 cubed, and that's equal to 2/3 times 8, and we're subtracting, so 1 to the 1/2 power is 1, 1 cubed is 1, so that stays the same, 1 to the 3/2 is 1, and then 2/3 times 1 is 2/3, so this would be minus 2/3 times 1 to the 1/2 cubed, which is minus 2/3. Okay, and now we just have to solve for this. So this would be 16 over 3 minus 2 over 3, and that's going to be equal to 14 over 3, or approximately 4.67. And again, we want the correct units. They're asking how many gallons leak out, so our units should be gallons. So this is similar to the previous question, or at least part of it. Okay, so now part B asks how many gallons of water are in the tank at time t equals 3. Well, now this is interesting, because we have the starting amount of water. T equals 0, it's 30 gallons. But then we have water entering and leaving the tank. So we need a way to calculate how much water is at t equals 3. So let's try to describe it in words. So the amount of gallons at t equals 3, well, that's going to equal the starting amount, how much water was in there initially, and then we'll add to that however many gallons were added in those 3 minutes, and from that we'll subtract out how much left the tank in those 3 minutes. So this would be amount at t equals 0, so the starting point. We'll add to that the amount pumped in, so this would be like by the faucet, and then from there we will subtract the amount pumped out. So this should make sense conceptually, right? We're just seeing how much net water is being added to our tank in those 3 minutes, but we also have some starting amount. Okay, so now we just need to solve this. So this is going to be equal to, well, there's 30 gallons at t equals 0, that's given to us. And then pumping in, we can handle that separately, but let's first look at how much is taken out. So we're given the rate, we want to get it into a volumetric quantity, so we'll just use the integral again, right? So this would be the integral from 0 to 3 of whatever we just did. So that would be square root of t plus 1 dt. And then for amount pumped in, we'll do the same thing. We're given that as a function. It's pumped into an underground tank at a constant rate of 8 gallons per minute. Right, so that's also a rate, similar to square root of t plus 1. So we'll do the exact same thing. Integral of 8 dt from 0 to 3. Okay, so that's what we're looking for here. And this we can solve pretty easily, actually. So this will be equal to 30 plus integral from 0 to 3 of 8 is going to be 24. If you don't trust me, you can try solving it on your own. But another way of confirming why it is 24 is because if 8 gallons are being added per minute and there's 3 minutes, 8 times 3 is 24 total gallons. But this is just a more complex way of expressing it, just making the relationship with an integral. And then for the last one, well, we just solved for that in the previous part. That was approximately 4.67. And now just solving for this gives us 49.33. And again, we need the appropriate units. This is asking for how many gallons of water, so our units would be gallons. And that's the answer to part B. Okay, so now we need part C. So this is asking us for the total number of gallons of water in the tank at time t, but we need an expression for that, which we'll call A of t. And well, we kind of already did that, didn't we? Like up here, for at least t equals 3, we expressed it in this form, but those words don't depend on what t it is. Like t equals 3, we could have changed this to t equals 5, t equals 10, and this logic on the right-hand side would have still stayed the same. And in fact, this equation right here, that would also be very similar. The only thing that would change are these limits. The limits were dictated by what time we were looking at. So our expression should be very similar to what we just wrote. So A of t is going to equal 30 plus the integral of something, of 8 dt, we'll handle the limits in a moment, and from that we'll subtract the integral of the square root of t plus 1 dt. And then, well, now we're finding the amount of gallons at time t. So here it was t equals 3. So perhaps where we see a 3, we should put a t. So we'll put zeros here because that's when time starts. And then we'll throw t's at the top. And so a little bit of an annoying thing here is in this second integral, we have a t in the limit of integration, but also in the integrand. That's not normally what we see in integrals, and it's a little bit messy. So what we can do is we can just change the variables in the integrand a little bit, since it doesn't depend too much on it. So we'll change it to an x and integrate it with respect to x. Because now we'll have the same value when we do the integral We're just substituting a t in now. So that'll be our expression for C. And now for D, we want to find the time in which the water is at a maximum. And we'll have to justify our answer. So the way we're going to do this is we're going to solve this by taking the derivative. Let me add a page. Right? So we recall that to find the maximum of a function, we need to take the first derivative and set it equal to 0. That's how we found the maximum and minimum of a function. That's in our extrema video if you care to look at that. So we're trying to find the extrema of this a of t. So 0 to t of 8 dt, minus 0 to t of the square root of x plus 1 dx. And so we're going to take the derivative of it with respect to t. So we have d dt of a of t, and we're taking the derivative, so d dt of 30 plus d dt of the integral from 0 to t of 8 dt minus d dt of the integral from 0 to t of x plus 1, but really x is kind of acting like t. Okay, so now we can solve for this. The derivative of a constant is 0. Here, we're taking the derivative of an integral with respect to t, so those sort of cancel each other out, and we're left with an 8. And then here, similar thing, this d dt and the integral with respect to t, those cancel out. So this would be minus the square root of x plus 1. And remember, we want this to equal 0 to find our extrema. So this would be 8 minus square root of x plus 1 equals 0. So 8 equals square root of x plus 1. We can square both sides, so 64 equals x plus 1, and that means x equals 63, or really t equals 63. And what we can do is we can check on both sides of this t equals 63, maybe 62 and 64, to see if this is actually the maximum, or maybe it's the minimum, or maybe we can run some other test, like the second derivative test. But for now, we'll just stick with this answer. That we can leave as an exercise for yourself to make sure you understand those concepts. But here, we're just doing what we've learned in the past, of taking the first derivative, setting it equal to 0, and finding the extrema. So that's the second problem. And again, it's about water flowing into a tank, so you'll see a theme with these types of questions. Okay, so now let's take a look at the next question. This one's much shorter. So a honeybee population starts with 100 bees and increases at a rate of n prime t bees per week. And then it asks, what does this quantity here represent? So by now we should be feeling pretty good about this, right? We're taking the integral of some rate. And as we've done in the previous problems, when we do that, that gives us what we called a volumetric property. So in this case, we have the rate of bees. So taking the integral of that will give us some quantity of bees. And we're doing it from 0 to 15 with respect to time. So now we're starting to think, okay, maybe it's counting how many bees are entering the population within these time limits from 0 to 15. And sure enough, we see 100 out front, which is where the population starts at. So perhaps we can start to formulate that this would represent the population of bees at time t. And, well, not at time t, because the limits are from 0 to 15. So, well, what is t given in? It's per week. So this would be the amount of bees added to the population in 15 weeks. So in all, it represents the total number of bees after 15 weeks. So this is a much shorter problem, but being able to see this equation and parse it for what it means, that's the important skill here. So always be looking at your limits, seeing if they're constants or in terms of t, and then seeing what you're taking the integral of. That'll help you out. So we got blessed with a nice question. Alright, this one's a little bit more interesting. So if the integral from 2 to 5 of 2 f of x plus 3 dx equals 17, find the integral from 2 to 5 of f of x dx. Okay, so this is going to be testing our integration properties. How well do we know our integration properties? So let's try writing out this left-hand side and seeing what happens. So we have the integral from 2 to 5 of 2 f of x plus 3 dx, and that equals 17. And we can see, like, let me highlight it. This is sort of what we want. So we want to get rid of that 3 and that 2 somehow, and those are constants which we know are nice to deal with. So we can sort of distribute this integral to the first and second term. So what I mean by that is we should remember a property that would say that what I'm writing now is equivalent to the first expression. So 2 to 5 of 3 dx, that equals 17. Right? That's just a property of integrals, being able to split them apart when you're adding them. And similarly, within your integral, if you have a constant, we can just bring that out. So this will be equal to 2 times the integral from 2 to 5 of f of x dx plus the integral from 2 to 5 of 3 dx. And that equals 17. And hey, this is what we're trying to look for, and it's right there. So let's treat this as a one massive variable and solve for it. So this is saying that the integral from 2 to 5 of f of x dx is going to be equal to 17 minus integral 2 to 5 of 3 dx. So we're just subtracting by this term on both sides. And then we're going to multiply it by a half because we want to get rid of this too. So now let's just solve for this, and that will give us the answer. So this is 1/2 of 17 minus, okay, so integral of 3 is 3x, and we're evaluating it from 5 down to 2. So that'll equal 1/2 17 minus, and we'll put big brackets. Now we'll use our fundamental theorem of calculus. So 3 times 5 minus 3 times 2. And then we'll just simplify this a bit. So 1/2 17 minus 15 minus 6. So that would be equal to 1/2 17 minus 9. And that will equal 4. And that should be our answer. So this question just testing how well do we know our integration properties. I don't know if that was visible at the very bottom there, but it should be now. And yeah, so just being comfortable with that, pulling constants out and splitting it apart when we see addition and subtraction, should be feeling comfortable with that. So this next question will also test our integration properties and how well we know it. So now we have a piecewise defined function, and it's broken apart when x equals 0. And we're trying to find this integral right here. And the first thing we'll notice is that the limits go from -2 to 1. And since 0 is in between this range from -2 to 1, a good idea would be to split apart the integral at that point. So what I mean by that is the integral from -2 to 1 of x times f of x dx, this is going to be equal to the integral from -2 to 0 of x times f of x dx, plus the integral from 0 to 1 of x times f of x dx. And the reason we do this is because now when we need this f of x, we need to put some quantity in there, now we're able to do that safely. Because for the left integral, we're only integrating when we're less than or equal to 0, So that would be this function, f of x equals x. And for the second integral, now we're going from 0 to 1, so we need this x plus 1 instead. So that's why we need to split it up there. So let's do the substitution. This is going to equal the integral from -2 to 0 of x times x dx plus the integral from 0 to 1 of x times x plus 1 dx. And now we solve. So integral -2 to 0 of x squared dx plus integral of 0 to 1, and then we'll distribute x squared plus x dx. Okay? So integral of x squared, that's 1/3 x cubed, evaluated from 0 down to -2. Let's throw some brackets around there just to keep it organized. And then we'll add to that integral of x squared is 1/3 x cubed, just as we said. And then the integral of x is going to be 1/2 x squared. So we'll add to that 1/2 x squared, but now we're evaluating it from 1 down to 0. Whoops, let me use red. Okay, so we can solve this now. We just got to plug and chug our way through it. So for this first one, we'll first plug in a 0. Whoops. So 1/3 0 cubed, and then we'll subtract from that 1/3 -2 cubed. And then the second brackets, first we'll plug in a 1, so 1/3 1 cubed plus 1/2 1 squared, and then we'll subtract from that the same thing but with zeros. And we should see that this term here is all zeros. Both of those terms go to 0, so we can cancel those out. This first term, that goes to 0. Now we're just left with the last few, so hopefully I don't make an arithmetic error here. This should be 8/3 plus 1/3 plus 1/2, which seems to be correct. And then if we simplify this, we should get 7/2 as our answer. So the last two problems hopefully were a little bit easier than the previous two, but the main thing here is knowing your properties of integrals. The last one was splitting up integrals based off of the integrand. Now we're splitting up integrals based off of the limits. So hopefully we're feeling more and more comfortable with this, and with more practice should be good to go. Excellent. So now we'll move on to something a little bit more daunting. We have a cosine function, and we're trying to find the average value of this function. So we're given an interval, which is always nice. We're given our function, and we want to find the average value. So I'll just write down that equation again. It's 1 over b minus a, integral from a to b of f of x dx. Okay? So this b and a refer to the interval that we are integrating on, and we're given that interval there. So we can just plug in our values. So 1 over 0 minus -4 times the integral from -4 to 0 of cosine of 1/2 x dx. And well, let's just take care of that fraction term out in front. That's just 1/4 integral of the same thing. So how are we going to attack this integral? Because we don't exactly know how to integrate that right away. Like, if it was just cosine of x, we could handle that. But cosine of 1/2 x, not too sure. But that should be a good indicator right there. If we know how to handle cosine of x, what if it was cosine of u? Well, we could do that too. The only difference between cosine of u and cosine of x is the letter. So why don't we do that with a u-substitution? So let's let u equal 1/2 x. du will equal 1/2 dx. And we'll substitute it back in. So now this integral is equal to 1/4 the integral of cosine of u du. And well, we can change our limits of integration. So now the bottom limit was originally -4. If we put -4 in here, we get u equals -2. And for the top integral, do this, or top limit, do the same thing. Should get u equals 0. Now we should be feeling good because we know how to integrate cosine of u. So that's going to be equal to, sorry. Oh wait, we haven't even finished this yet. We still need to handle this properly. I didn't do this properly. Du equals 1/2 dx. So that means dx equals 2 times du. There we go. Oh, that's better. Always got to be careful with that. So we can bring that 2 out in front, and that'll be 2/4, which is the same thing as 1/2. Integral from -2 to 0 of cosine of u du. Okay, now we're good to go. So integral of cosine is equal to sine. So this would be equal to 1/2 sine of u. And we'll evaluate it from 0 down to -2. And this just comes down to using the fundamental theorem of calculus. So that would equal 1/2 sine of 0 minus 1/2 sine of -2. Well, sine of 0 is 0, so this first term will go to 0. So we're just left with -1/2 sine of -2. And looking at this, none of the answer choices match what we have. That's not good. A couple of them are close. This one here is pretty close. It doesn't have the minus sign inside. This one here is pretty close, but both terms are positive. The rest don't make too much sense, so maybe we can eliminate these. And the way we get to the final answer is we take advantage of the fact that sine is an odd function. So we have to recall that sine of -x equals negative sine of x. That's just a property that sine has. So with that in mind, this simplifies to negative times -1/2 sine of 2. And that equals 1/2 sine of 2, which would be e. So a little bit tricky here, but we can see that with most of the work, we were able to eliminate these 3 answers pretty quickly. At least c should have been eliminated really quickly because it has a cosine in there and we're taking the integral cosine. These other 2, the coefficient didn't match, and then deciding between these 2, we just had to know that strange fact about sine. But it's still very helpful to remember, so this fact right here, always good to know. So that's that. Now we have this question here, trying to solve for k given an integral. And well, there's a couple of ways to solve for this. The easy way out, well, I don't know if it's easy, but the simple method would just be to plug in all of those values for k, and then see which one equals 12. In my opinion, the better way is to solve that integral with k still in it, and then hopefully have an easier equation with k. So let's do it my method. So we have the integral from 0 to 2 of 2x cubed minus kx squared plus 2k dx. And we want this to equal 12. So we're going to integrate with respect to x, because that is what it tells us to do. But there's a k in there, so we have to treat k like a constant. So we shouldn't be raising k's power and then dividing by that. No, we're only going to do that for x. So integral of 2x cubed is 2x to the 4th divided by 4 minus integral of kx squared. We're going to raise the power of x by 1 and divide by that new power. So see how k is remaining untouched. It's just a constant. Even though it's a letter, it's just a constant. And for this last one, integral of 2k, we're integrating with respect to x. So this would be 2kx. And this is being evaluated from 2 down to 0, and we want this to equal 12. So let's use the fundamental theorem of calculus. But now where we see an x, we will put in a 2 or a 0, again, leaving the k untouched. So this will equal 2 times 2 to the 4th over 4 minus k times 2 cubed over 3 plus 2 times k times 2 minus, now we'll just put in a 0 over 4 minus k times 0 cubed over 3 plus 2 times k times 0. We want this to equal 12. Nice that all of these terms go to 0, so we don't have to worry about them. Now let's just solve for this here. So this first term, 2 times 2 to the 4th is 2 to the 5th, which is 32. 32 divided by 4 is 8, minus, well, that's going to be 8k over 3. We'll add to that 4k. We want this to equal 12. Let's bring this 8 to the other side. So this would equal now 4. And then 4k minus 8k over 3. Well, 4k is 12k over 3. Minus that 8k over 3 would give us 4k over 3. And now we can just say k equals 4 times 3/4, which is equal to 3. So that's our answer. So it would be a shame if we tested all those values of k in the order given to us, because we would have to test all 5 of them. And even now, it would probably be a good idea to plug in k equals 3 and make sure that we have the correct answer. But I don't feel like doing that right now. So you can do that and make sure that we're correct. But we are correct. So yeah, don't be afraid of integrating things, even if there are other variables. Just treat them as constants unless otherwise stated, but I don't think it'll be any other case because, yeah, it'll most likely always be constants like that. So, yeah, it might look a little bit nasty, but it's helpful in the long run. Okay, so now we have this question, second to last question. We're almost there, but it's good practice. We're given a function. First part is to find the derivative of it. That should be pretty doable. So that's, I mean, this is just a throwback to when we were learning about derivatives. So let's just do it off to the side. We're given f of x equals square root 25 minus x squared. Square root functions are nasty, so let's just rewrite it as a power, which some may argue is more nasty, but it's easy when we're doing derivatives. So f prime of x, well, this seems like a type of power rule, chain rule type thing. So we'll first bring down the power, multiply this by 25 minus x squared, decrease the power by 1, and then we have to multiply by the derivative of the inside, so that would be negative 2x. So it's been a while since I've done some derivatives. Hopefully you're still keeping up with your skills on that, but if not, it's always good to practice. We could simplify this a little bit more as like negative x times 25 minus x squared to the negative 1/2, or even negative x over the square root of 25 minus x squared. You could do that. I like to leave my answer like in this form, especially on an AP exam, because what I have in the box is correct. If you make any mistakes in your simplification, you will get points off, which is not good. So just leave it in that form. It's better for you. So now we want to write an equation for the line tangent to the graph at x equals negative 3. Okay, wow, we're really needing to think about what this stuff means. Tangent lines, it feels like forever ago. So recall that the first derivative gives us the slope of the tangent line at a specific point. So we want it at x equals negative 3, so let's plug in negative 3 in here. So f prime of negative 3 is going to equal 1/2 25 minus negative 3 squared to the negative 1/2 times negative 2 times negative 3. Okay, so now we just need to solve for this. So this will equal 1/2 25 minus 9 to the negative 1/2 times 6. I think. I hope. Yeah. So 1/2 now we can probably make this a fraction. So this would be the square root of 25 minus 9, which is just 16. So let's just write a 16 in there, times 6. So this would be 1/2 times 1/4 times 6, and that's equal to 3/4, right? So that's just the slope of the tangent line. We still need something else. So we could use point slope form to describe the equation of a line. We have the slope, we just need the point. Well, if we're looking at x equals -3, we should probably find the y-coordinate for that. And to do that, we can plug it back into f of x. So f of -3 is going to equal 25 minus -3 squared. That's equal to the square root of 25 minus 9, which is equal to the square root of 16, equals 4, right? So that'll be our y-coordinate. Sorry, I shouldn't have boxed that. So now we know that we have a function which has a point at -3, 4, and the slope of the tangent line at that point is 3/4. So let's put it together. Point is -3, 4. Slope is 3/4. So now we just have to write the equation of a line. So we'll do y minus 4 equals 3/4 x plus 3. So this is point slope form. Hopefully you recall how to do that. If not, the idea is that we take the y-coordinate of our point and subtract it from y, and that's equal to the slope multiplied with x minus the x-coordinate. That's what we call point slope form. So very helpful to still be familiar with this from algebra, and if you're not, I highly encourage remembering it because they often like to give us the equation of a line, and this will help you out. So that's part B. Part C is asking us about continuity. We're given a function g, and we want to see if the function's continuous at g at -3. Like, why are we doing all this stuff? This was forever ago. It's for review. We have to be on top of these things and not forget these things. So let's do it. Continuity. For this, we have to use the definition of continuity, which means taking the limit from both sides. And we're looking at -3. So part C. We'll start by taking the limit from the left. So the limit, as x approaches -3 from the left, well, see, our function is piecewise at -3. So we have to look at, to the left of it would be when we're less than -3. So that would be f of x. So g of x equals f of x, and f of x equals this up here. So we're finding the limit as x approaches -3 from the left of the square root of 25 minus x squared. And we can do this using direct substitution, so that would be equal to 25 minus -3 squared. We just solve for that, that's going to equal 4. So now we need to test the limit as x approaches 3, or -3, from the positive side, from the right. So now when we're to the right of -3, g of x equals x plus 7. So let's find the limit of that, and again we can use direct substitution. Equals 4. So since the two limits equal each other, we say that yes, it is continuous. So yes, it is continuous at x equals -3. Great. So hopefully this stuff's coming back to you in case you forgot it. And D, part D, finally we have an integration question. Feels like we haven't done that in forever, but I'll add a new page and I'll just rewrite the integral. So we're finding the integral from 0 to 5 of x times the square root of 25 minus x squared dx. Okay, so we're looking at this, and hopefully you're thinking u-substitution. And the reason for that is we see an x squared whose derivative will cancel really nicely with this x term here. So we want a u that hopefully has that x squared in it. So let's just try to use this entire 25 minus x squared. So u equals 25 minus x squared. Du equals negative 2x dx. And we do have limits here, so we'll be sure to take care of those in just a moment. So let's just rewrite this integral. We'll worry about the limits later. X times the square root of u now, and then dx is going to equal du divided by negative 2x. Let's take care of the limits now. So if we put in a 0 for x here, we get 25 minus 0 squared, which is equal to 25. So our bottom limit is u equals 25. Our top limit, when x equals 5, u equals 0. So that's our top limit. We should see that this x cancels with this x, and we have this negative 1/2 term here, which we can factor out. So let's just rewrite it, make it look a little bit prettier, factor that term out, integral, bottom limit is 25, top limit is 0. We'll write u to the 1/2, because that's easier to integrate, times du. And this we can handle. So this will just be a simple power rule. So negative 1/2 times u to the 3/2, and then we have to divide by 3/2, which is the same thing as multiplying by 2/3. We're evaluating this from 0 down to 25. Okay, so this 2 cancels with that 2, which is really nice. We're left with negative 1/3 u to the 3/2, and let's just plug it in. So this would be negative 1/3 times 0 to the 3/2 minus negative 1/3 25 to the 3/2. Okay, well 0 to the 3/2 is equal to 0, so this entire first term will go to 0. Whoops, I need the red marker. And then this negative signs cancel each other out. So now we're just left with 1/3 25 to the 3/2, which we can rewrite as 25 to the 1/2 cubed. So 25 to the 1/2 is equal to 5, just the square root of 5. And then we're cubing that, so that would be 125. So this is equal to 125 over 3. And that's our answer. So a nice little u-substitution problem right there to round things out. One more question, and this one comes from an AP exam, and it'll require a little bit more review, but always great to review. So, Johanna jogs along a straight path for 0 less than or equal to t less than or equal to 40. Johanna's velocity is given by a differentiable function v. Selected values of v of t, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. Use the data in the table to estimate the value of v prime of 16. Excellent. So v of t is the rate, the meters per minute, so that's like her velocity, as it mentions. So v prime of t would be the derivative of that. So what does derivative mean? Slope, right? We're thinking slope of the tangent line. Well, okay, so 16 falls somewhere in between these 2 points. And we're given, 2 separate points here, so we can just use those 2 points to get an estimate of what the slope will be. So we'll do 240 minus 200 divided by 20 minus 12. So that's equal to 40 divided by 8, which is equal to 5. And then we want to have correct units. So v of t is meters per minute. We're taking the slope of that with respect to minutes. So this would be meters per minute squared. Cool. Using correct units, explain the meaning of the definite integral that in context of the problem. So we have to be a little bit careful here. So we're taking the derivative of velocity. And when we do that, we usually associate that with distance or displacement. But now we have to be a little bit careful because there's a huge difference between distance and displacement. So, since we're taking the absolute value of velocity, that will be the distance traveled. And the way we can imagine this is we have some sort of graph here showing like her velocity with respect to time. So this would be like velocity. No, sorry, I think it should be the other way around. The way we would find displacement is we would take this area and we would take the area underneath and we would subtract them to get displacement, because her velocity is positive going in one direction, and then she turns around because her velocity is negative, and then we check the total displacement. For absolute value, that would be equivalent to finding the same graph, but now that hump becomes positive, so that would be the total distance traveled. Because now we can think that instead of turning around, she continues going straight, and that would be distance. So that's a quick little sketch of why it's distance, but that's why we have to be careful. So I'm not going to write that out, but the answer would be like the total distance that Johanna jogs in the interval from 0 to 40. It's measured in meters because it says to use correct units. And then it asks us to approximate that value using a right Riemann sum with the 4 subintervals indicated in the table. Golly, Riemann sums, that's been a while. So let's copy this. Let me do it a different way. Copy, okay. So for Riemann sums, I always like to draw things out. So we have like, this is one axis, and then we have a data point at 0, 0. We have something at 12, 200. We have 20, 240, so that's somewhere here. 24, negative 220 is down here. And then 40, 150 is like here. Right, so that's sort of like what the graph will look like. I guess I'll connect them with lines just to make it look decent. And then we're trying to use a right Riemann sum for this. But the important thing is we're trying to calculate the absolute value of v of t. So this data point down here, we have to make that positive because we're taking the absolute value. So let's change that up a little bit. That'll come down here. And now let's just redraw our lines. And now we have to use our right Riemann sum. So what would the rectangles look like? With the right Riemann sum, we want the right corner of the rectangle to touch the function. And we're using 4 rectangles, I think the problem mentioned, and we need to use these points in the table. So the rectangles would look something like this. So this would be the first rectangle, this would be the second rectangle, the third, and then the fourth. Okay, and now we have to, use the data points. So this point here is at 12, 200. The next one is at 20, 240. This one's 24, 220 because we took the absolute value. And the last one is 40, 150. So with that in mind, the width of the first rectangle is 12, and its height is 200. The second one has width 20 minus 12, which is 8, and its height is 240. Third one has width 4, 24 minus 20 is 4, height is 220. Last one has width 16 and has height 150. So now we just have to take the product of all of these. So this would equal 12 times 200 plus 8 times 240 plus 4 times 220 plus 16 times 150. I won't make you watch me. Actually, I will make you watch me scroll through this. So this is 2400 plus 1920 minus 880 plus 16 times 150 is 2400, I hope. And then we just have to add and subtract these all together. So this will equal 7,600 meters. And just making sure that our units are correct, we're trying to find the distance that she traveled, because that's what we said that this quantity represents, and meters matches that unit, so we're good. Cool. So Bob is riding his bicycle along the same path. We have another velocity equation for Bob, and now we're asked to find Bob's acceleration at time t equals 5. So acceleration is the derivative of velocity, so we should take the derivative of b of t. So if b of t equals t cubed minus 6t squared plus 300, then we want to find b prime of t. So first derivative 3t squared minus 12t, and we want to find the acceleration at t equals 5, so we just plug in a 5. B prime of 5 equals, oh boy, 3 times 5 squared minus 12 times 5. That's equal to 75 minus 60. So that will equal 15. We have to have the correct units again. So meters per minute squared, right? Because we're dealing with acceleration. And now we're on to the last part of the problem, which asks for the average velocity on the interval from 0 to 10. So hopefully we're feeling good with average values of functions now. So our function now is this one up here, b of t, because we're finding average velocity. So again, just make some room. The formula is 1 over b minus a, integral from a to b, of b of t, dt in this case. So a and b are given here by our interval. So this will equal 1 over 10 minus 0, which I'll just say is 1 over 10. Integral from 0 to 10. B of t is this right here, so t cubed minus 6t squared plus 300 dt. And now we just have to solve this integral. This will be 1/10 integral, or we don't need the integral yet, or anymore. So this will be 1/4 t to the 4th using the power rule, minus 2t cubed, plus 300t, evaluated from 10 down to 0. Fundamental theorem of calculus time, 1/10. First we'll plug in the 10, so 1/4 10 to the 4th, minus 2 times 10 cubed, plus 300 times 10, minus, and now we plug in a 0, 1/4, 0 to the 4th, minus 2 times 0 cubed, plus 300 times 0, running out of room. But luckily all of these terms go to 0, so we don't even need them anymore. And we're just left with the first thing to deal with, which is a little bit annoying, but it's okay. And this is going to be, let's see, 1/10 times 10 to the 4th is that number, divided by 4. 2 times 10 cubed looks something like that. And then 300 times 10 is that. And then we can simplify this a little bit, but we don't feel like doing that. I'll just give you the answer. Hopefully you get the idea. 350 meters per minute. That's our final answer. Make sure that our units match, or at least make sense. We're trying to find average velocity, so this is why we have these units as our units for velocity. And that concludes our session on practice problems with integrals. Hopefully this was helpful. We went through a ton of stuff today, practicing everything from u-substitution to average values of functions to Riemann sums and derivatives, so everything encapsulated in one. Hopefully this was good practice for you. And yeah, thanks for watching. We'll be learning a lot more about integration. We've explored the surface of integration, but there's still so much more to learn. So those will be in the future videos. But for now, be happy with what you know. You've learned a lot. Be very proud of yourself. Pat yourself on the back. And yeah, so enjoy the rest of your day. and happy studying. Good luck and take care.